In section 7.4, we're looking at equations with rational expressions and graphs. Our objectives are to determine the domain of the variable in a rational expression, solve rational equations, and recognize the graph of a rational function. Determining the domains of rational equations. Find the domain of the equation. For part A, we have the equation 5 over x minus 1 over 6 equals 11 over 2x. Since we're instructed only to find the domain of the equation, we're not actually solving the equations. We do want to look and see if there are any restrictions on the domain. Typically, the domain for rational equations is all real numbers, except for whatever values of x would make the denominator equal to 0. Since the first fraction appears as 5 divided by x, we can say right away that x cannot equal 0. If we were to solve this equation and get 0 as a solution, that would be an extraneous solution because 0 is not part of the domain of this equation. And looking at the fraction on the right side, you're dividing by 2x. You can say 2x also cannot equal 0, and the only way that would happen is if x is equal to 0. So again, x cannot equal 0. The domain is all real numbers except for x equal to 0. Let's look at part B. The equation is 3 divided by x minus 1 minus 2 divided by x plus 1 equals 6 divided by x squared minus 1. Let's look at any restrictions on the domain. Let's find any values of x that would make the denominator of any of those fractions equal to 0. Well, the first denominator is x minus 1. We can say that x minus 1 cannot equal 0. That is going to be a restriction on the domain. And by solving this for x, by adding 1 to both sides, we see that x cannot equal a positive 1. Looking at the second fraction, we see x plus 1 in the denominator, so that entire denominator cannot equal 0. That's a restriction on the domain. By subtracting 1 from both sides, we see that x cannot equal negative 1. On the right side of the equation, we have the denominator of x squared minus 1. So we can say x squared minus 1 cannot equal 0 as well. The x squared minus 1 is a polynomial that can be factored. So the factors of x squared minus 1 are x plus 1 and x minus 1. So those two the product of those two factors cannot equal 0. And by using the zero factor property and setting each of those factors equal to 0, x plus 1 cannot equal 0, so again, x cannot equal negative 1. And if we set x minus 1, say that cannot equal 0 as well, x cannot equal positive 1. We can see that x equals 1, x cannot equal 1 appears twice here, and the x cannot equal negative 1. So those are the two restrictions on the domain. Caution on solutions. Caution: when each side of an equation is multiplied by a variable expression, the resulting solutions may not satisfy the original equation. You must either determine and observe the domain or check all potential solutions in the original equation. It is wise to do both. Let's solve this rational equation. 5 over x minus 1 over 6 equals 11 over 2x. And our first step here is to rewrite the equation so that we don't have these fractions. And to do that, we find the least common denominator. Looking at each of the denominators, we see x, the LCD, is going to have each factor of every denominator represented. So the LCD is going to have an x. The LCD is also going to have a 6. And the LCD is also going to have a factor of 2x, which is already part of this LCD. Now, once you find that LCD, you multiply both sides of the equation by the LCD, and something really nice is going to happen when you do that. This equation that started off really complicated with all these different fractions will end up being a simplified equation that doesn't have any fractions. And that always happens when you can multiply both sides of a rational equation by the LCD. Let's distribute the 6x to each term on the left side, and we have 6x times 5 over x. Well, that can be simplified because the x terms will divide out and you'll get 6 times 5, which is 30. Now if we distribute 6x times the 1 over 6, and I'm putting the minus there, minus 6x times 1 over 6. And what's nice about this one, again, the 6th denominator will divide out, and this can be represented as x times 1, or x. So 30 minus x is the simplified form of the left side of the equation. On the right side, we're going to distribute the 6x as well. In fact, we're going to multiply 11 over 2x times 6x. Now this can simplify as well. The 2 will go into 6 3 times, and the x in the denominator will divide out with the x in the numerator. So on the right side of the equation, we get 11 times 3, which simplifies to 33. Now we have this nice equation, no more fractions. We can work through and solve this equation. We can subtract 30 from both sides of the equation, and we get negative x equals 3. And then by dividing both sides of the equation by negative 1, we see that x is equal to negative 3. Now this is our solution to the original rational equation. We do want to check your solution, and we want to make sure that we are being cautious about any values of x that would make the denominator equal to 0. We're cautious about any restrictions on the domain. So in our check step here, we're taking the in our check step, we're taking our original equation and replacing the x with our answer of negative 3. So we get 5 divided by negative 3 minus 1 over 6 is equal to 11 over 2 times negative 3. By simplifying this, we get negative 5 over 3 minus 1 over 6 equals 11 divided by negative 6, or negative 11 over 6. To see if these two fractions will combine to give you negative 11 over 6, you want to get a common denominator. And the missing factor in the first is 2, so we can multiply the numerator and the denominator of the first fraction by 2. When we do that, we get negative 10 over 6 minus 1 over 6, and that does check to equal negative 11 over 6. So we have confirmed that our answer of x equals negative 3 is a valid answer by substituting it back into the original rational equation. All right, let's solve this rational equation by first finding the LCD. The LCD is going to have the factors of each of the denominators. The first denominator is x minus 1, so that is part of our LCD. The second fraction denominator is x plus 1. That's also part of our LCD. And on the right side of the equation, the denominator is it can be factored into x plus 1 and x minus 1. And since those two factors already appear in our LCD, we don't need to add them again. Now we're going to multiply both sides of the equation by the LCD. So on the left side, we're going to multiply by x minus 1 times x plus 1. And on the right side as well, we're going to multiply by x plus 1 times x minus 1, the LCD. Now this is going to simplify our equation. When we multiply the LCD by the first fraction, we get x minus 1 times x plus 1 times the first fraction of 3 over x minus 1. Now notice the LCD includes that x minus 1 factor, so the x minus 1 in the denominator will divide out with the x minus 1 part of the LCD. The result is 3 times x plus 1. Now we're going to multiply the second equation by the second fraction by the LCD, So that's going to look like minus the LCD of x minus 1 times x plus 1 times the fraction 2 over x plus 1. Now the x plus 1 denominator will divide out with the x plus 1 that's part of the LCD, and the result would be minus 2 times the quantity x minus 1. Let's multiply the LCD on the right side, and you will get 6 over x squared minus 1, which factors into x plus 1 and x minus 1, times the LCD x plus 1, x minus 1. And again, the nice thing here, that denominator factor of x plus 1 will divide out with the x plus 1 factor in the LCD. The denominator factor of x minus 1 will divide out with the LCD factor of x minus 1. So our right side of the equation simplifies to 6. Now let's distribute each of these on the left side of the equation to get 3x plus 3. Distribute that minus 2 to get minus 2x plus 2 is equal to 6. Notice how we have this nice simple equation that can be solved using our standard algebra expressions here. Let's combine like terms, and we get 3x minus 2x, or x, plus 3 minus plus 2 is plus 5, so we have x plus 5 is equal to 6. By subtracting 5 from both sides, we get x is equal to 1. So that is our solution to the rational equation. However, we always need to check our answers. When you check, you replace the x in the original equation with what you found in your solution. When we do that, we get 3 divided by our solution of 1 would be 1 minus 1 minus 2 over 1 plus 1 equals 6 over 1 squared minus 1. Notice we have a problem here. When we simplify in the check step, we have 3 divided by 1 minus 1 in the denominator. So that's 3 divided by 0. We have a problem here. So that means 1 cannot be a solution, since 1 is actually a restriction on the domain. So we say that is an extraneous solution, meaning algebraically we were able to arrive at x equals 1, but when we go through and check, we see that it cannot possibly be a solution. So we call that an extraneous solution, and the original equation has no solution. So when you're working through solving equations with rational expressions, and you're multiplying both sides of the equation by an LCD, there is a possibility that the final answer may not check. So it's always important to check your solutions. Let's solve this rational equation. Before we multiply both sides by the least common denominator, we want to write each fraction in factored form. Our first fraction becomes 4 over the factored form of a squared minus 9 is a plus 3 and a minus 3, the difference of 2 squares. The second fraction becomes 3 over 2, and the factored form of the trinomial is a minus 3 and a plus 1, the factors of negative 3 that add up to negative 2, and that is equal to the right side in factored form is a plus 3 and a plus 1. So we want to make sure our LCD has each factor represented for each of those denominators. So our LCD will begin with a factor of a plus 3 and a factor of a minus 3. So a plus 3, a minus 3. We will also include a factor of 2 and a factor of a plus 1. This a minus 3 is already represented, so we'll have 2 and a plus 1. And for the last fraction on the right side, we have a plus 3, which is already part of our LCD, and a plus 1, which is already part of our LCD. We're going to multiply all of these fractions by the LCD, and in the next step that will eliminate any fractions altogether. So if we multiply the whole left side of the equation by the LCD, which is 2 times a factor of a plus 3, a factor of a minus 3, and a factor of a plus 1. Okay, we're going to distribute that to each term on the left as well as the term on the right. We're going to multiply that by 2 times a plus 3, a minus 3, and a plus 1. So we will have some simplifying when you multiply the LCD times the first term. That a plus 3 will divide out with that a plus 3, and that a minus 3 will divide out with the a minus 3 factor. So the result would be 2 times a plus 1 times that numerator of 4, with the other factors canceling out. And then when we divide out the common factors, distribute the LCD to the second term, the 2 will divide out with the 2, the a minus 3 will divide out with the a minus 3, the a plus 1 will divide out. So the remaining factor that's left over, part of the LCD, is your a plus 3 times 3. And on the right side of the equation, we will be able to simplify the a plus 3 factor with the a plus 3, the a plus 1 with the a plus 1. So what we have left is going to be 6 times 2 times the factor a minus 3. So notice in this step we end up with an equation that doesn't have any fractions. Now we're going to simplify, distribute. We have this 2 times this 4 is 8. 8 times a plus 1 minus 3 times a plus 3 equals 12 times a minus 3. Now we can distribute 8 to get 8a plus 8. Distribute the minus 3, careful with the signs here, minus 3a minus 9. Distribute the 12 on the right to get 12a minus 36. Now let's combine like terms and simplify this equation. We can, on the left side we have 8a minus 3a, and that's 5a, and 8 minus 9 is a negative 1, equals 12a minus 36. We can then subtract 5a from both sides of the equation, and we can also add 36 to both sides of the equation to end up with 35 on the left side is equal to 7a on the right side. And then when we solve this by dividing both sides by 7, we get a equals 5. And you can go back and check to make sure that this is a valid solution by plugging in 5 into the original equation. Also notice that the 5 would not be a restriction on the domain of these rational expressions. So when we check by plugging in 5 on the left side for a, we get 4 divided by 5 squared minus 9, and minus 3 over 2 times 5 squared minus 2 times 5 minus 3. All of that on the right side should equal all of that on the left side should equal on the right side 6 over 5 squared plus 4 times 5 plus 3. All right, so let me get a calculator and check the solution. All right, so when you plug in the 5 and simplify, the first fraction becomes 4 over 16, the second fraction becomes 3 over 24, and the fraction on the right is 6 over 48. So you can double check that 4 over 16 minus 3 over 24 does equal 6 over 48. So our solution to this equation, again, is a equals 5. The strategy in solving this type of equation is to rewrite it in factored form, multiply both sides by the LCD, and we end up with an equation that doesn't have any more fractions. And then finally work through, solve that problem, and check your final answer. Let's look at solving this rational equation by multiplying both sides by the LCD. The LCD is going to have a 2x plus 1 factor, since that's part of the first denominator. It's also going to have an x factor, which is part of the second denominator, and the 2x plus 1 in the last fraction is already represented. So let's multiply both sides of this equation by the LCD. When I multiply the left side by x times the quantity 2x plus 1, and I multiply the right side times x times the quantity 2x plus 1, using the distributive property and simplifying, when you distribute to the left side, the 2x plus 1s will divide out, and you'll be left with x times 4, or 4x on the left side. When you distribute on the right side, the first x will divide out, so you get 2 times the quantity 2x plus 1. And when you multiply the second fraction on the right, the 2x plus 1 factor will divide out, so you're multiplying by x. So you would get minus 8x squared. Let's use a distributive property and simplify this equation. By distributing the 2, we get 4x equals 4x plus 2 minus 8x squared. We can simplify this equation by subtracting 4x from both sides. And we get 0 is equal to 2 minus x squared. 2 minus 8 x squared. So this is a quadratic equation, and one way to solve quadratic equations is by factoring, or we can use the quadratic formula. Or we can use the square root formula. So if I factor out a common factor of 2, I get 2 times the quantity 1 minus 4x squared. And 1 minus 4x squared is a difference of two squares that can be factored with 2 as the first factor, 1 minus 2x, and 1 plus 2x. We're going to set each of those factors equal to 0. If you set 2 equal to 0, that's not going to help you find the solution, but we can set 1 minus 2x equal to 0, and by adding 2x and dividing by 2, we get x equals 1/2 as a possible solution. And by setting 1 plus 2x equal to 0, subtracting 1 and dividing by 2, we get x equals negative 1/2. We do want to make sure that both of these answers work in the original problem, so don't forget that check step. We're going to check in the original equation, each one separately. Let's check x equals positive 1/2. When you plug in 1/2 into the left side of the equation, you get 4 over 2 times the half is 1, 1 plus 1 is 2. On the right side, you get 2 divided by 1/2 minus 8 times 1/2 over 2 times 1/2, which is 1 plus 1, which is 2. So let's simplify this. 4 divided by 2 is 2. 2 divided by 1/2 is 4. 8 times 1/2 is 4. Divided by 2 is 2. So 2 does equal 4 minus 2. So we know that x equals 1/2 is a solution to this rational equation. We also need to check to see if negative 1/2 is a solution to this rational equation. When we plug negative 1/2 in for x on the left side, we get 4 over 2 times a negative 1/2 is negative 1. And negative 1 plus 1 is 0. Oh no, we cannot divide by 0. So even though algebraically we were able to get x equals negative 1/2 as a solution, when we go back to check it, we see that's a restriction on the domain. So that is an extraneous solution. We're not going to include that. The only real solution to this equation is x equals positive 1/2. Let's look at the graph of our basic rational function f of x, which is equal to 1 over x. Well, one thing we can do when we're graphing and we're not familiar with the types of functions yet is to set up a table of values, and I usually like to try some negative values, let's say -2, -1, 0, +1, +2, just to get an idea of what this graph looks like. We're plugging each of these x values into our function, which is 1 divided by x. When you plug in -2, you get 1 divided by -2, or -1/2. So -2, -1/2 is a point that's on the graph of the rational function f of x equals 1 over x. If we plug in -1, we get 1 divided by -1, which is -1. So -1, -1 is another point that's on this graph. We plug in 0. However, when we plug in 0, we get 1 divided by 0. Oh no, we can't do that. That is undefined. So you will find that there is something very interesting happening to the graph when x equals 0. We have a vertical asymptote. So a vertical asymptote is this imaginary vertical line where the graph will approach but will never actually touch that vertical line. So we see the behavior here, like when x is closer and closer to 0, but on the left side, these y values start going towards negative infinity. Now we can try some values on the right as well. Plugging in 1, you get 1 over 1, which is 1. So that corresponds to this point over here. Notice the scale on this particular graph. There's every 3 units, there's a mark in the x direction, but there's only 1 mark in the y direction for the scale. So just pay attention to that. Now if we plug in 2 into this rational function, you do get a half, so that corresponds to this point here. You will also see that with this vertical asymptote behavior, you have this horizontal asymptote, this flattening out. And that occurs when these x values get larger and larger and larger, the y values will get closer and closer to 0. And in both directions. As your x values go towards the left, the y values will also get closer and closer to 0, but from below. So our basic graph of this rational function, f of x equals 1 over x, has both a vertical asymptote and a horizontal asymptote. Now this graph g of x equals -2 over x minus 3 also has a vertical and horizontal asymptote. The vertical asymptote occurs here at +3. We have this vertical line where the graph will approach but won't ever actually touch that vertical line of x equals 3. Now notice that is the value that would make the denominator equal to 0. If we plug in x equals +3, and evaluate the denominator, you get 3 minus 3, or 0. So you can also make a table of values here and find values as, for example, when x is equal to 4, when x is equal to 5, and so on, to see that behavior. Or when x equals 2, or x equals 1, and so on. You can see that behavior of the graph as you approach x equals +3, that vertical asymptote. This also has a horizontal asymptote where the graph will tend to flatten out as it gets closer and closer to 0.